Here is another example. A mixture of 5.00 times 10 to the power of negative 3 moles of gaseous H2 and 1.00 times 10 to the power of negative 2 moles of gaseous I2 is placed in a 5.00 liter container at 448 degrees Celsius and allowed to come to equilibrium. Analysis of the equilibrium mixture shows that the concentration of gaseous Hi is 1.87 times 10 to the power of negative 3 molar. Calculate Kc at 448 degrees Celsius for the reaction. We start with an ice table. Before we complete it, we need to translate the information in the question carefully. 5.00 times 10 to the power of negative 3 moles and 1.00 times 10 to the power of negative 2 moles are initial number of moles of H2 and I2 respectively. How do we know this? We infer this from the phrases is placed in a 5.00 liter container as well as allowed to come to equilibrium. To be put in a container implies that the reaction hasn't yet begun, but will begin once the reactants come together. By being told that H2 and I2 were allowed to come to equilibrium, we are to think that they weren't at equilibrium prior to this point. So it means the number of moles of each is the initial number of moles used at the beginning. But in the ice table, we are to use concentration. We need to convert number of moles into concentration. We divide number of moles by volume of the container, which is given as 5.00 liters. Moles per liter is molar. There is no mention of the concentration of Hi at the start, nor is it stated that Hi is present at the start. So we take it that initial Hi concentration is 0 moles per liter. The concentration of Hi of 1.8 times 10 to the power of negative 3 molar is not the initial concentration. Rather, it is the concentration at equilibrium based on it being obtained from the analysis of the equilibrium mixture. Next, for row C, since there is no Hi at the beginning, the reactants H2 and I2 will have to react to form Hi. How much of each? We don't know. So we let the unknown concentration be 1x. Why 1 in 1x? Because the stoichiometric coefficient of H2 and that of I2 are each 1. Since H2 and I2 will be consumed, we use minus. Thus we write minus 1x for both H2 and I2. For Hi, plus 2x will be formed. Plus is used since Hi, which does not have any existence at the start, will grow into existence. 2 of plus 2x is obtained from the stoichiometric coefficient of the equation. Now for row E, add the information from row I to the information from row C for each cell. Recall that the question provides the equilibrium concentration of Hi. Thus equate 2x with 1.87 times 10 to the power of negative 3. Solve for x. Next, we write the Kc formula. Kc equals the square of Hi concentration divided by the concentration of H2 and the concentration of I2. Substitute all the terms in row E into this Kc expression. Then plug in the value of x into the equation to get the value of Kc. Here is another example. 1 mole of gaseous molecular iodine undergoes reaction to give 2 moles of gaseous atomic iodine. For this reaction, Kc equals 3.76 times 10 to the power of negative 5 at 727 degrees Celsius. 1 mole of gaseous molecular iodine is injected into a 2-liter glass box at 727 degrees Celsius. What will the concentrations of gaseous molecular iodine and gaseous atomic iodine be when equilibrium is attained? We write the Kc formula and complete the ice table by carefully translating the information given into mathematical language. We plug in the equilibrium concentration terms involving x taken from the E row of the ice table into the Kc expression. Then we equate this to the Kc value given. We get the square of the whole of 2x divided by 0.5 minus x equals 3.76 times 10 to the power of negative 5. This time around, it can be potentially time-consuming to solve for x, since we are faced with an equation that eventually reduces to the form of ax squared plus bx plus c equals 0. Fortunately, there is an easier way which we can use to solve for x, the approximation method. We notice that kc is very small due to the factor 10 raised to the power of negative 5. Since kc is small, x must be small compared to 0.5. Thus, 0.5 minus x is approximately equal to 0.5. Why? A small kc means the numerator is a lot smaller than the denominator. If the denominator, which is the concentration of molecular iodine, is larger, it means the formation of molecular iodine is more favorable than that of iodine atoms. Thus, the system is reluctant to convert large amounts of molecular iodine into atomic iodine. It only allows tiny amounts of molecular iodine to turn into atomic iodine. Thus, the change in concentration of molecular iodine, which is set as minus x, is rather small. X must necessarily be tiny compared to 0.5. So if a tiny number is subtracted from 0.5, 0.5 barely changes in value. Thus, 0.5 minus x is approximately 0.5. In general, if kc is smaller than 10 to the power of negative 3, that is 0.001, we assume kc is small. Then the approximation method can be used. Now that the denominator no longer has minus x, solving for x becomes easier. The square of the whole of 2x means 2x times 2x, that is 4x squared. 4x squared divided by 0.5 equals 3.76 times 10 to the power of negative 5. On the right-hand side of the equation, 3.76 times 10 to the power of negative 5 may be rewritten as 3.76 times 10 to the power of negative 5 divided by 1. Cross-multiplying, we get 0.5 times 3.76 times 10 to the power of negative 5, as well as 4x squared times 1. Dividing both sides of the equation by 4, then taking the square root of both sides of the equation, we get the value of x. Substitute this value of x into the equilibrium concentrations of I2 and I.